We're going to move on to chapter 6. This is one of the last chapters that we're going to cover, but we're now going to start to delve into a lot more thinky side of math. So remember, what we've been doing so far in this class was the very first couple weeks we learned all of these proof techniques. With those proof techniques under our belt, now we're able to start to look at different mathematical structures. But notice that underneath almost all of these so far have been the idea of sets. Remember, sets is this building block of mathematics. We can base a lot of things off of sets because it just makes sense, right? If I have a collection of objects, I can just define that as a set. So a collection of numbers, that's going to be a set, right? So, or a collection of letters, whatever. So sets is the thing that we're basing almost all of our mathematics off of. So far we looked at just the basic idea of sets, set operations, and all of those things. And then we define functions based off of sets. And then we define relations, again, based off of the idea of sets. And then now we look at sizes of these sets. We'd like to understand how big these are. So we're going to, chapter 6, we're going to look at finite and infinite sets. So this first section on natural numbers, we'd like to define natural numbers in terms of sets. Now, obviously, you're thinking, well, I already know, right? I thought we all agreed that the set of natural numbers, this is going to be the set containing 1, 2, 3, 4, and all of these numbers, right? Yes, that makes sense. But when we start to delve deeper into mathematics and we try to prove things, how could we really know that these are all of the numbers in the natural numbers? How do we have some formal definition of what the natural numbers are? Because this ... really isn't a formal way of describing anything. So to be able to help mathematics have a firm foundation, we need to have some type of beginning step to make assumptions for the natural numbers. So what we have here are called the Peano Postulates. The Peano Postulates is the axiom that we're going to, or the axiom system that we're going to use to define the natural numbers. So what an axiom is going to be something that we just believe to be true. So if we're thinking about axioms right here, so axioms, these are going to be things that we assume are true, but can't prove. So there's certain things in this class that we haven't proven, and I've just said, just assume that these are true, right? We said, assume that when you add two integers, you get an integer. If you multiply two integers, you get an integer. How do you prove that? Well, we have no idea, right? That actually is extremely difficult to figure out. How do you even start to prove that for any integer, I add another integer, and I get an integer? So you could try that if you want, and you realize that, well, what is the definition of an integer? How could I use that? So same thing with a natural number. Notice with natural numbers, if I add 1 to a natural number, I always get a natural number. Well, how could you prove that? Well, you'd have to use the definition of a natural number. Well, what is the definition of a natural number? Well, we're going to use Peano's postulates. So this is the axiom system that we're just going to assume that this is going to be true. So this says that there exists a set, this n. Now, this is not, at this point, this is not the natural numbers. This will become the natural numbers after all of this, but there's just some arbitrary set that we just happen to call this fancy n. And it has this element 1 in this. So there's a set that 1 is an element of. Then we're going to define this function that's going to map this set to itself. And it must satisfy these 3 properties. So the first property that this must satisfy is that there is no n in the natural number, or it's no n in this set, such that s of n is equal to 1. Okay, now we're like, okay, maybe you're lost at this point. This function, think of this as what's called the successive function. So we're looking at successive numbers in the natural numbers. So this function is going to basically say the next number. So there is no number whose next number is 1 in this set. Or in other words, once we think about this set being the natural numbers, we're saying that there is no number that is going to be less than 1. 1 is going to be the smallest natural number. Then the next statement says that the function s is injective. So this is a one-to-one function or an injective function. That means if you have two different numbers, they're going to get mapped to two different numbers. Right? So we're saying that if there's two different numbers, the successive function is going to map those to two different numbers, which makes sense, right? If I have 2 and I have 3, the successive number in our intuition is going to be 3 for 2. And then for the number 3, the successive function would be 4, right? So you get mapped to different numbers if you start out with different numbers. And then this statement here that says that if G is a subset of the natural numbers, if that's a set, and if we assume that 1 is that, then if G is in there, if this G is in our set G, then the successive 1 is also going to be in that set. So this is where the idea of the successive function really comes from, is this definition here. We're basically saying that if a number's in there, if a number's in this set, then the next natural number will basically be in that set. So that's what we've defined here. And so we start out with 1, and so what we're defining is the successor to that is 2, and the successor to that is 3. And so all of these together form the set of the natural numbers, and these are things that we can't prove. We're just going to assume that they're true to be able to define the natural numbers. And so as the conclusion of all of this, n, this is really the natural numbers. So this set that we've defined this way, this is the natural numbers. All right. So there's not really homework on this. This is just to get you to start thinking about what we're going to be talking about for the rest of class, is that we're going to really delve deep at certain points into the underbelly of mathematics and understand what are all of these hidden assumptions that we've just all agreed upon at this point, and how do we really have a firm foundation for mathematics.